on this.
Our speaker is Skrypnyk from.
Хорошо.
You see the title, Asymmetric Variable Separation for the Clebsch model. And okay, you are welcome. Let's begin. I kindly ask everyone to switch off microphones, and it may happen that I'll have problems with connection because I'm not in Moscow and is in a hotel, and internet here is not stable. So if I disappear, then Alec Verbovensky will play my role. So let's begin.
Okay, good afternoon. My name is Skrypnyk, and I will make a talk on asymmetric variable separation for the Clebsch model. First of all, I want to thank the organizer and the Joseph for inviting me. You are what are you looking on? You see me? Do you see my screen?
Yes, we see. It's perfect.
Okay, good. So this talk is based mainly on our not very recent paper with Franco Magri, published in the archive 5 years ago, and partially on to our recent papers with Franco and Yuri Fedorov, which are in some sense development of this first paper. The plan of the talk will be the following. First of all, I will make a brief introduction. Then I remind the general facts about separation of variables in integrable Hamiltonian systems. Describe 3 main modern methods in this field: the magic recipe of Sklynin, the big Hamiltonian approach, the method of differential conditions. Then I will describe the Clebsch model itself. Then I will pass to Weber-Neyman subcase of the Clebsch model and separation of variables for it, which is well known. I remind you because it will be necessary in some sense. Then finally, I will come to asymmetric separation of variables for the Clebsch model, and we'll discuss separated variables, the reconstruction formula, and the Abel type equation. Then I will comment on the solution of the Abel type equation, that is on the Abel-Jacobi inversion problem for the constructed quadratures, give a kind of geometric Weber-Neyman type interpretation for the obtained asymmetric solve, and briefly conclude. Instead of the introduction, I will start with several, say, motivational questions and comments. First of all, why separation of variables in the Hamiltonian-Jacobi sense is important? Why we are considering this? It is important because it is the main method of the integration of the classical equation of motion for integrable Hamiltonian systems, at least those with finite number of degrees of freedom. It is also used while solving quantum integrable models, as it is well known since the papers of Sklynin. Probably I will not, during my talk, I will not show you these references. I will show and comment on the references at the end of the talk. Okay. Second question that may arise, natural for non-expert. What is the state of art in this subject? Well, there exists, say, 3 main approaches to the variable separation. A classical one, going back to the papers of Steckel Levi-Civita and Agostinelli, and developed later in the papers of Sergio Benanti and his school. And there are two modern approaches. They are magic recipe of Skrypnyk and the Hamiltonian approach of Magre, Falco, and Padron. The classical approach of, say, Benanti, etc., is somewhat restricted. They work only with Hamiltonian systems on the cotangent bundle. That is when the momenta and coordinates are globally defined. Two modern approaches cover much more wide class of integrable models, but unfortunately they are also far from being finished, since they have many problems to solve yet. I will explain later on. Now, another natural question: why the Clebsch model? Well, the Clebsch model is the only integrable case of the Kirchhoff model of the motion of rigid body in the liquid, for which Hamilton-Jacobi separation of variables was unknown for almost 1.5 centuries. It was known only on special submanifolds, where it is equivalent to the Weber-Neumann model, which we'll discuss later. So it is really a really difficult problem, and we will see that its solution demonstrates some qualitatively new properties. Here I need to say also that there is a kind of separation of variables for the Clebsch model in general. There is an old paper of Kötter, but the variables of separation of Kötter are not canonical ones, and we are not with Kötter. We are not in the Hamilton-Jacobi settings. So let me pass to the definition. And first, I will remind some general facts on Hamiltonian-Jacobi separation of variables. So we will consider a Hamiltonian system with n degrees of freedom, determined on to n-dimensional symplectic manifold, which is embedded as a Poisson manifold in the Poisson manifold as a submanifold of some Poisson manifold as a level surface of M Casimir function Ci, and possess n independent commuting first integrals I yod. Poisson commuting. We are considering classical case. To find Hamiltonian-Jacobi separated variables means to find, at least locally, a set of coordinates xi p yod such that exist n relations, so-called equations of separation of the form 1, where the coordinates xi p yod are assumed to be quasi-canonical, that is, the Poisson brackets have the form 2. Here we have index 1 near the Poisson bracket, because we will consider also second bracket, and we will consider the Hamiltonian structure later on. So such a definition of variable separation is in such a general settings is probably due to Skrypnyk. It is possible to show that it is really equivalent to the Hamilton-Jacobi variable separation, which is studied in the course of mechanics. So now why this equation of separation and why condition 1 and 2 are important? They're important because using these two conditions, it is possible to derive equation 3. Equation 3 in their turn lead to the following differential and identity form, which we call Abel type equations. This Abel type equation permit integrate this equation of motion. Upon integrating this differential, we obtain some expression of t as function of x, and the inversion of this formula, so-called Abel-Jacobi inversion problem, will give us the solution of x in terms of times t. Here t yod are times corresponding to the integral I yod, that is parameter along its Hamiltonian floor. So in some sense, equation 4 are the final point for separation of variables and the starting point for the integration procedure. Let me now describe the state of arts in the subject. And first of all, I will say a couple of words about the magic recipe of Skrypnyk. Well-known magic recipe. This magic recipe is connected with the case when our Hamiltonian system under consideration possesses Lax-Pay formulation. So the magic recipe was proposed by Skrypnyk in 1995, and we remark that its roots of this approach, at least in the classical case, go back to the papers of Flaschka, McLaughlin, Abler, Novikov, and Veselov, and some other papers. Well, the magic recipe states that in the Lax integrable case, all equations of separation should coincide with one spectral curve of the Lax matrix. That is, all equations of separation have the form phi. And the coordinates of separation coincide with the poles of properly normalized eigenvectors of Lax matrix. Using this proper normalization, one can construct the coordinates and moment of separation as zero of certain function b of u and the values of another function a of u in these zeros by formula 6. Unfortunately, in the general case, the magic recipe of Skrypnyk doesn't answer the question what the proper normalization should be. That is why it is more precise to call the magic recipe to be kind of magic conjecture, due to the fact that in general there is no concrete recipe of how to construct the proper normalization of the Baker-Heisen of their function, that is of the eigenvectors of Lax matrix, or equivalently how to construct in general the functions b of u and a of u. Another restriction of the method is the condition that all the equations of separation are the same and coincide with the spectral curve of one Lax matrix. As we will show in the present talk, this is sometimes too strong, the requirement, and it doesn't hold true in some cases. That is why it is desirable, even if we are treating a Lax integrable case, to have some alternative methods of separation of variables. Two of such methods I will briefly describe below. So, first of all, the method of vector field zeta in the Hamiltonian approach of separation of variables. This method was proposed by Magriff, Falkio, and Pedroni in 2001. And it permits to construct the coordinates of separation xi for the given Hamiltonian system, starting from the certain data of the Poisson geometry. In more details, if you assume that there exists a second Poisson bracket with index 2 compatible with the first one, that is, any linear combination of these two brackets is a Poisson bracket, then we have a so-called Hamiltonian structure, and the bracket with index u is called Poisson pencil sometimes. We denote the Casimir function of this Poisson pencil by ck of u. They will naturally also depend on arbitrary parameter u entering in this bracket, and we will assume this Casimirs to be polynomial in this parameter u. That is, we assume so-called Gelfand-Zakharevich assumptions. In this case, there is a theorem of Magro-Falker and Padroni that if we consider vector field zk k from 1 to m that possess the property 7, for property 7, here you see, I hope you see all of them. If the roots, all roots of the equation defined by the formula 8 are functionally independent on the general conjoint orbital of the first Poisson structure, then these roots xi are the coordinates of separation for the considered Hamiltonian system. Let me say also that I will call polynomial the root of which are the coordinates of separation to be the polynomial separator or separating polynomial. So on the one hand, we have a nice theorem, a nice formula, nice answers. But unfortunately, this approach has a difficult part. In order to construct this polynomial S of u, 8, number 8, you have to find all vector fields zeta k, which satisfy nonlinear PDE. All these conditions with the vector fields, at least conditions set 7b and 7c are nonlinear PDE. So in general, how to resolve this in terms of initial dynamical variables, it is not clear. In some cases, however, the task is a bit simplified, and one needs only one vector field zeta k for a certain index k in order to define separating polynomial S of u. So the corollary of previous theorem says that if we have m-1 common Casimirs of the two brackets 1 and 2, then the roots of the equation 9 whereas present only one vector field zeta m are the coordinates of separation. Hence, in the simplest case when all but one Casimir of two brackets are common ones, the problem of construction of separating polynomial is reduced to the problem of finding of only one vector field zeta m, which satisfy instead of conditions 7, simpler conditions 10. All this condition involve only one vector field zeta with index m. And here xm is a Hamiltonian vector field of the Casimir Cm with respect to the second bracket. With respect to the second bracket, Casimir of the first bracket generate non-trivial flow. So nevertheless, even equation 10 or more precise equation 10b and 10d are nonlinear PDE for the components of the vector field zeta m, and they are in general difficult to solve. One of our observation is a possible approach to solution of this system, which I will discuss below. So as the problem, one problem of this method I already indicated. The problem is that it is difficult to solve all these systems of nonlinear PDE in order to construct the polynomial separator. And another approach is that in general, the method provides only coordinates xi and does not provide the conjugated momenta pi. In order to obtain this conjugated momenta, we will use another method, which I call the method of differential condition. The method is due to Franco-Magri, and he calls this condition Kovalevsky condition because he has found them studying the Kovalevsky integrable top. So I will expose the method only in the simplest case and only in the simple trivial dimension n is equal to
Пропал звук.
Пропал звук, да, я тоже ничего не слышу. Тарас.
Может, это с интернетом?
Значит, не у меня проблемы, да? Пропал не только звук, но пропал и докладчик, по-моему. Я его не вижу.
Я думаю, что это с интернетом у него.
У него, видимо, да. Интересно, сам он понимает или нет?
Internet connection problems.
Ага.
Well, I have to show again the screen. One moment, please. So share screen. Share screen. Here we have share. Do you see it?
Ага.
Okay, I have started to explain the methods of differential conditions. Have you heard this part? Joseph.
Can you repeat this page?
Yes,
Fine.
Page 8.
Okay, page 8. Yes.
Yes. Okay.
Okay, page 8. The method of differential conditions, which was invented by Franco Magri relatively recently and is not yet published in complete generality. This Franco also calls this method the method of Kovalevsky condition because he has invented it, studying the Kovalevsky top, integrable top. I will explain this method in the simplest case, n equal to m equal to. I will put afterwards first integral I will call h, and second integral I will call k. I introduce also in natural way two derivatives, point and prime of any function f on the phase space by the formula 11, and the following proposition hold true. Assume that our separating polynomial has the form 12. With vector field z at 2, satisfying condition 10. That is this condition with m equal to 2. Then the function s1 and s2, the coefficient of this separating polynomial, will Poisson commute, formula 13, and satisfies the following differential equation, 14a and 14b. First equation is linear, and the second equation is quadratic. So the first fact and the second fact that the corollary of this proposition is the following. Let x1, x2 be the roots of separating polynomial, defined as above. Let then the function x1, x2 Poisson commute and satisfies the following differential equations. Equation 15. This equation are also the sufficient condition together with Poisson commutativity for the function x1, x2 to be the separated coordinates. They also, with the help of this conditions, we can also prove the following important theorem, which we have proved with Franco in all variant of our paper. So let the coordinates xi satisfy condition 15. and Poisson commute. Define the functions of grade I by the formula 16. Then in the coordinate system consisting of the functions x1, x2, aka kappa, c1 and c2, we will have that phi I does not depend on x yod, formula 17, and the function pi defined by the formula 18, we have here integral formula, as a momenta canonically conjugated to the coordinates x. So integrating equation 18, we obtain pi as some function of xi, aka kh, c1 and c2, and consequently we obtain as a final point some equations of separation, which may be different for different indices 1 and 2, as we will see below. So now I can finally pass to the Clebsch model. What is a Clebsch model? This is a particular case of the Kirchhoff model of the motion of a rigid body in the liquid, which can be written on the in the Lie algebraic terms on the Euclidean Lie algebra S3, rather on its dual space. So we have 6 coordinates S alpha T alpha, which satisfy standard Poisson bracket 19 of the Euclidean Lie algebra. This bracket possesses 2 Casimir functions C1 and C2 of the form 20, and 2 quadratic functions E1 and E2 given by the formula 21, 22 are Poisson commuting integral of motion. Say H is Hamiltonian and K is integral. So evidently, the system is completely integrable. The dimension of the corresponding phase space a level set of Casimir function is 4, and we have 2 Poisson commuting integrals. The equation of motion can be easily written with, for example, with respect to Hamiltonian H, they have a form 23. Here, T1 is a time corresponding to this Hamiltonian. Another important fact is that there is a second structure, second Hamiltonian structure, second Lie Poisson structure, having the form 24. Containing the parameters iota, which are free parameters in our Hamiltonian, playing the role of anisotropic parameter. This bracket contains these parameters iota alpha, but in the case when they are not 0, the algebra 24 is isomorphic to S quater. Thus, isomorphism is achieved by the substitution 25. In such a way, the considered model is isomorphic to the so-called Schottky-Fram model on S quater, known also as Monaco model. We observe that the function C1 is a common Casimir for both brackets, and the Hamiltonian K, integral K, is a Casimir function of the second bracket. So, and for the second bracket, the integrals are function H and C2. So the Poisson pencil of the above bracket, given by the formula 26, possesses the following Casimir function: C2 of U, organized as follows, and C1 of U, which is simply C1, a common Casimir of all structure in the Poisson pencil. Let me mention also that we are interested in the completely anisotropic case when all parameters of anisotropy are not equal. Let me go to the description of interesting and well-known subcase, so-called Weber-Neyman subcase of the Clebsch model. It is possible to show that on the coadjoint orbit when C1 is equal to 0, the Clebsch model is equivalent to the Weber-Neyman model. The corresponding coadjoint orbit might be viewed as a cotangent bundle over the sphere S2, embedded into the 6-dimensional linear space with the coordinates Q1, Q2, Q3, P1, P2, P3 by the equation 28. Here, the coordinates q1, q2, q3, p1, p2, p3 possess canonical Poisson brackets. Parameterizing the algebraic variables as in the formula 30, we will have that the Hamiltonian H of the Clebsch model acquires the Weber-Neumann form, form 31, which describes the motion of the particle on the sphere in the quadratic potential. So let me also remind the separation of variables of Weber-Neumann subcase of the Clebsch model, because it has some analogy with what I will be telling below. So well known for more than a century is the separation of variables of Weber and Neumann. Separating polynomial in this case is written by the formula 32, and its two roots satisfy the equation of separation 33. Two equations, both equations are the same, where the coordinates xi pi are the canonical ones. So let us briefly explain that this separation of variables is in fact the Hamiltonian one. On the surface C1 is equal to 0, the normalized Euler vector field 34 satisfy all the condition 10. In more details, this condition 10 have the following form. Form 35, and it is straightforward to check that the vector fields that do indeed satisfy this condition. So that is why I define the separating polynomial by the formula, by the previous formula, acting on the Casimir C2 of U. And we have formula 36, which indeed coincide with the well-known polynomial 32 after making it monic. That is making the highest coefficient that to here be equal to 1. So the moment of separation are obtained using the formula 18 using this integral formula and using this theorem. In this case, it is not difficult to do directly. So having seen this, let us pass to our result on the asymmetric separation of variables for the Clebsch model. First of all, why asymmetric? Because we will have two different curves of separation, and everything will be very asymmetric in the separated variables x1, x2, and separated momenta p1, p2. So we want to do basically the similar thing as we had previously for the case of Weber-Neumann. We would like to have as a formula 37. With some vector field Z2, but we would like that this vector field Z2 will call simply Z, that this vector field satisfy the condition 35, not only on the surface C1 equal to 0, but everywhere in our 6-dimensional linear space. So, of course, in this case, Z2 given by the formula 34 will not work, and we have to find the wanted and needed vector field. That is why we will write general vector field on 6-dimensional linear space given by the formula 38. This vector field has components, arbitrary function in general, which will be subtracted by which will be how the English word is given will be should satisfy some conditions in order for the vector field Z to satisfy condition 35. So how to find these components? And so here goes our one of our main, say, tricks. We don't want to resolve the nonlinear PDE for the components A alpha, B alpha, and that is why we have assumed that the vector field zeta is a very special one. It annuls its own component, so satisfy condition 39. By other words, this specific requirement transform differential equations 35C simply to the algebraic equation. Instead of the equation 35C, we have four equations: 40A, 40B, 40C, and 40D. And a normalization condition for the vector field given by the equation 35D give us linear equation in the coefficients B1, B2, B3, I1, I2, S3. Formulas for the F, for the F. So having this equation, we were able to solve them, and the solution is given by the following proposition. Proposition 9. The equations 40 have the following generic solution given by the formula 41, where the function V alpha entering into this formula are given by the formula 42, C alpha as a constant that depend on the anisotropy parameters, and V is the function of S alpha T beta satisfying the following equation 44, which is consequence of course of equation 40F, and lambda is general normalization factor, which is easily found using the equation 40. So we have this generic solution, and let me say only that in principle we can put lambda to be equal to 0 because the normalization of separating of the vector field zeta does not change the root of the corresponding separating polynomial. So another important fact is that this equation 44, viewed as equation for the function V, is a rational equation, which after the rationalization produce equation of the 8th order in the function V. That is, we have 8 solutions for the function V, 8 possible solutions in terms of the function S and T. And of course we cannot solve the 8th order the equation of 8th order explicitly. So every calculus that we have accomplished, and I will show below, something should be made with implicit function we satisfying equation 44. And well, here another trick was to introduce intermediate coordinate system consisting of the function phi1, phi2, phi3, g1, g2, g3, defined by the formulas 45, 46. And the definition is of course connected with the vector field zeta and its components. So these coordinates are very useful in all the calculations. In particular, in their terms, we formulate our main theorem that the roots of polynomial separator 37, this polynomial, for the vector fields with zeta with the components given by the formulas 41, 43. Have the following explicit form: x1 is equal to v itself, this function v that enters into the definition of all the objects, and x2 is expressed rationally as a function v, and our auxiliary function f1, f2, f3, g1, g2, g3. And the same thing holds for the momenta canonically conjugated to the coordinates x1, x2. We have quite explicit formula, quite simple. And having this formula, we can state that this object satisfies the curves of separation of the genus 3, having the form 49 and 50. These are two different algebraic curves, not equivalent, but both of them have the same genus. The genus is 3. Well, now. First of all, I want to emphasize once again that we have come, starting from this Hamiltonian approach, we have come to separation of variables with two different curves of separation. To the best of my knowledge, previously there have been no example of such a kind, at least for the, say, Lax integrable Hamiltonian systems, to the class of which belongs also the Clebsch model. So now a couple of words about the proof of this theorem. The first way to prove this theorem is simply to prove that not only conditions 35C, 35D are satisfied, but also condition 35A, 35B are satisfied. So in such a way we'll be
Опять пропали.
I should repeat something. I have not noticed.
Is it my problem or problem of the speaker? I cannot hear him.
Do you hear me?
Now, yes.
Strange. I have not seen the emission of internet or something. So
Well, let's proceed.
I can repeat something if it is needed. So should I repeat? Or should I continue? Joseph.
Oh, well, please continue. It seems Joseph has sometimes problems with internet.
Okay. So if you prove also 45A, 35A, 35B, will be in the framework of Magri-Falke-Quadrani theorem, and it will be okay. Another possible proof is to prove that the coordinate xi given by this formula Poisson commute and satisfies the condition 15. This condition, then to find function fe and honestly integrate and obtain the equation of separation. The second way and the third way, which is technically much more simple, I will sketch the proof in this spirit. The direct proof. The direct proof, why it is possible, because we have in fact almost explicit modulus effect that we the function v is defined implicitly, almost explicit formula, and we can try to prove the canonical form of the Poisson brackets and the equation of separation. This is done directly. In order to do this, first of all, we see we should write the separating polynomial S of u with the concrete vector field zeta, and see that this polynomial is factorizable. It is factorized into linear nu multipliers with root 6(1), x2 presented in the formula 47. Then we calculate the Poisson brackets among the new functions g alpha, f beta, and v. It is not very simple, but still manageable expressions. We substitute, and we check that these momenta are indeed canonically conjugated to the above x1, x2. Finally, using the explicit form of variables pi xi in terms of function g alpha of beta, and we re-express in this terms initial dynamical variables and then also integrals of motion and Casimir functions. We obtain the following not very simple but still manageable formula, and taking into the account our constraint, which is remarkably simple, constraint 44, our main constraint defining function v, which acquires in this terms very simple form. We immediately show that modulo this constraint, the following equation of separation holds true for the given x1, x2. Here, of course, simplifying fact is that x1 is the same thing as v. So here we have in fact v plus y1, v plus y2, v plus y3, and the same thing as seen on the same radicals v1, v2, v3, etc. that are presented everywhere. So this is basically how one can prove this theorem directly, or one can prove the theorem using the theory two methods I have introduced above. Here we have to say a couple of words about so-called reconstruction formula. What is the reconstruction formula? In order to be able to solve the equation of motion for the initial dynamical variables, in our case S alpha T alpha, we have to be able to express S alpha T alpha explicitly as function of the separated variables x1, x2, p1, p2, and values of the Casimir functions c1 and c2. And a nice thing is that despite the fact that function v and as a consequence the coordinates x1, x2, p1, p2 we cannot find explicitly. The formulas of inversion say the reconstruction formula we can find explicitly in terms of these coordinates. These are formula 53, A53B, and these objects satisfy a three Poisson brackets if x1, x2, p1, p2 are canonical. Due to our zero, one can also check it by hand or with Maple. So we see that the reconstruction formula are profoundly asymmetric in the variables x1, x2, p1, p2. In particular, here we have everywhere radicals of x1 plus iota alpha, x1 plus iota beta, etc. But x2 enters in the rational manner. So the final point of the procedure are the so-called Abel type equations, or Abel type equation written in the differential form, using the general formula 4, which is, let me remind, sorry, which is written as follows. And the explicit form of the equation of separation given by formula 49 and 50. By simple substitution, we obtain the following Abel type equations. Here T1 and T2 are times corresponding to the Hamiltonians H and K. It is useful to transform them to a bit more standard from the algebraic geometry form. For this purpose, one changes the variables, like in the formula 56. And in this case, the separation curves are simplified to the form 57, 58. And the Abel type equation are written in the form 5960. We observe that the differential W1, W2 of the form 61 participating in our Abel type equation are two holomorphic differential on the curve 57, while the differential V1, W2 large are holomorphic differentials on the curve 58. This factor, this radical is important because with this radical, after all the periods of this of the differential becomes commensurable, and that is why our new Abel type equations 5960 can be inverted in terms of meromorphic functions of times. They lead to a well-defined so-called Abel prime-map from the product of the curve C times K. Here we denote this curve C, this curve K, to a two-dimensional prime subvariety of the Jacobian of the curve K. Here prime varieties enters into the game, not the usual Jacobians. Moreover, it can be shown that separated coordinates are expressed in terms of the so-called higher order theta function on the prime variety of the curve K. This is done in the second part of our recent work with Franco Magri and Yuri Fedorov. Well, important remark, in contrast to the standard Abel map, the Abel prime map is not one-to-one. A full preimage of a point in the prime variety consists of the 8 pairs of the points on the curve C times K. The coordinate of these 8 points can be identified with the 8 set of separating variables for the Clebsch system, connected with 8 different solutions, V1, V2, etc., V8 of the main constraint equation 44, which is the equation defines the function V. So this enables to derive a new set of functional solutions for the original variables as alpha t alpha. They can be expressed as symmetric function of coordinates of the 8 points on the curve C, while the latter function can be written in the terms of higher order theta function, which solves the problem of inversion of the Abel prime map. So by other words, the map from the prime variable, prime subvariety was a time sleeve to the curve C and K is 1 to 8. But then map from the curve C times K to the initial phase space S alpha is 8 to 1. So in the result, we pass this ambiguity, and we have we connect one time T1 1 point in the prime variety with times T1 T2 with 1 point in the initial phase space with the coordinates S alpha T beta. At last, I will say a couple of words about so-called Weber-Neyman interpretation of our asymmetric solve. For this purpose, we need to extend the phase space of the Clebsch system, C6 or R6, endowed with the mentioned above Poisson pencil. To extend it, for this purpose, we define elliptic curve by standard Weierstrass-Kubik, formula 63. Let A hat be its unramified 4-to-1 covering, on which the function V alpha are correctly defined. Then we can prolong the Poisson pencil into extended phase space, which is a product, simple product, direct product of P and A hat, with the coordinate S alpha T alpha V by the formula 44, one bracket, and the same formula for the second bracket. So we obtain a new Poisson pencil on the extended phase space. We obtain that this extended Poisson pencil has two common Casimir's, C1 for all brackets of the pencil, and C'1, which is simply zeta of C1, and the quadratic Casimir C2 of U as previously. So evidently, the vector of we have vector fields x hat, x h hat, x a k Hamiltonian vector fields on p hat, which have essentially the same form as on the space P without a hat, and pass to the Clebsch vector field after the canonical projection. Under such the definition, the constructed solve for the Clebsch model can be interpreted as solve for the extended Clebsch model, but not everywhere, but only on the special symplectic leaves in P hat, given by the equation 65. So like in the Neumann case, we have C'1, not C1, but C'1 is equal to 0. C'1 is exactly zeta of C1, that is our constraint. In such a way, the obtained separation of variables is interpreted as Weber-Neumann type separation of variables for the extension of the Clebsch model. As our main constraint equation 44 for the function v is interpreted in this case as zero-level set of the Casimir function C'1. And our strange condition that the vector field zeta annuls its own components is reduced modulo the normalization of the vector field zeta hat to the requirement that the extended vector field zeta hat has simple form 66. With components depending only on the coordinate v living in the extension. In such a way, this viewpoint provides geometric interpretation of asymmetric separation of variables and geometric interpretation for the main constraint equation 44. Nevertheless, regardless of the interpretation, the proposed separation of variables exhibits the following qualitatively new properties. First, it has different curves of separation C and K. That is, we are out of the magic recipe of Skrypnyk. Second, the genus of the separation curve is 3. It is larger than the number of degrees of freedom, equal to 2. Third, in contrast to standard Abel map, the corresponding Abel prim map from C times K to prim variety K is not one-to-one. All these three properties are very non-standard for the usual separation of variables connected with algebra geometric integration scheme. At last, some natural questions that may arise in the context of the presented results. Is there any symmetric separation of variables for the Clebsch model with two separation curves being equal? And second, is there any other, except for the Clebsch model, examples of the Lax integrable models with different separation curves? The answer to both questions is positive. As for the first question, in our paper 24 in Journal of Geometry and Physics, we have constructed symmetric separation of variables for the Clebsch model on the product of two curves C. As for the second question, using the B-Hamiltonian equivalence of the Clebsch and Schottky-Fram model, we have constructed a symmetric separation of variables on C times K also for Schottky-Fram model. Moreover, we have recently obtained a symmetric separation of variables for several systems with 2 and 3 degrees of freedom that are not equivalent neither Clebsch nor Schottky-Fram models. This results in new, and soon I hope to publish them. This, in fact, brings me to the end of my talk. I only want to show you the references. First references to the paper of Kirgov. Unfortunately, I have not found a precise year, but it is more than 150 years ago. The Clebsch paper on the Kirgov model has been published precisely 150 years ago. Then have been two papers of Weber and Neumann, published in 1877, 78, and 18. So probably here's mistake. Probably here should be 1879. And the paper of Kyoto, published several years afterwards, about very specific very specific separation of variables not connected with Hamiltonian Jacobi formalism, not canonical one. Then the papers of Flashkamp, McLaughlin, Albert, Novikov, Vasilov, etc., that were some predecessors of the magic recipe of Skrypnyk. The paper of Luke Hain that has considered in the spirit of algebraic geometry the properties of the curves K and C and their prime varieties. The papers of Enolsky and Fedorov, recent papers that has considered the Kyoto separation, Kyoto non-Hamiltonian Jacobi separation of variables in spirit of the algebraic geometry. I'm finishing, yes. Skrypnyk paper where he has introduced the magic recipe. Then a series of classical papers of Stekelli, Vicivita, Agostinelli, and the subsequent papers of Benenti and his school were the standard approach to the separation of variables to do the system on the cotangent bundles has been considered. Then two papers of Falco, Magri, Pedroni, Falco and Pedroni on the Hamiltonian separation of variables. A recent paper of Franco Magri about the differential. He calls them Kovalevsky type conditions for the separation theory. The Gelfand Zakharevich paper on the special Poisson pencils, and at last paper, our papers with Franco, which was basic for me today in the archive. My subsequent two papers, one of them in theoretical and mathematical physics, connected with asymmetric solve for Schottky-Fram models, and my paper in Journal of Geometry Physics connected with symmetric solve in Clebsch model. And at last, two recent preprints with Yuri Fedorov and Franco Magri. In the first one, the new interpretation of the symmetric solve was proposed. This is a development of the paper 22. And in the second one, the theta functional solution for the constructed Abel type equation have been found. Thank you for the attention.
Okay, thank you very much. In spite of all the problems, we managed. So, questions, remarks, you're welcome to begin. No question?
I see here Rafael Vitolo. He already has.
Hi.
Hi.
Hi, Taras.
Hi.
I would like to ask a question,
But
but it's not a mathematical question. I just would like to know if you can leave the slides to, well, okay, privately or publicly available.
To send you the slides?
I mean,
sure, I can.
Your slides here, if you
Yes.
can, well, at least I am interested. If you can send them to me, I would be great.
Sure. I will send you this PDF file. It is more or less everything is contained in these papers 22, 25, and 26.
Okay, okay.
But well,
But it's
yeah,
a very nice summary, so it's nice
it
to
is a
have it.
summary. Yes, I will send you this. Sure.
Thank you very much.
It was my pleasure.
Because you see, the video is, well, you need to, how to say, to look at the whole video to find a particular point, while if you have the slides, you can find it quite quickly.
Sure, Rafael, I will
Thank you.
send you with pleasure.
You can also save your slides on the website of the seminar. It will be a good idea.
If you can send it to the seminar address, your file, it will be perfect. Will you do it?
Well, I can send it to Joseph, to you, and you.
Or to me, it doesn't.
It
doesn't matter.
I will send the file to you, and you will put it.
Yes. Okay. Okay. Thanks a lot. More questions? More remarks? Okay. Thanks a lot. So we meet in a week, and the next Wednesday speaker will be Zhenya Kharapova. Have a good week. Have nice holidays, weekend, and well, see you in a week. Bye bye.
Nice holiday. See you next week.
Bye bye.
Ciao.
Have a nice
Ciao,
first
bye
of
bye.
day. Bye bye.
Bye, Taras. Thank you.
Okay, good luck.